Hi, Doug DeHaven here with the Carnegie Science Center, and I am in the exhibit design department. My particular role, mechatronics. I work where electronic, mechanical engineering, and software all come together. And recently, we were tasked with a fun project. Now, the design department for the Science Center isn't exclusive to the Science Center. We often will design exhibits for other museums, and this was the case. They came to us with a ball pit ball problem. So these are the balls that you would have like in a play pit, like a Chuck E. Cheese or something like that. And they wanted us to throw these a long distance. Now, the thought for this was, it was called Pinball Falls. It's a long staircase, happens to be about 24 feet long, about 9.5 feet high. And we needed to throw these. Well, the problem we ran into is these are very light. They're full of air. For that reason, they're safe. Well, the problem with that is you need mass to accelerate. F equals ma, force equals mass times acceleration. So if we don't have the mass and we need to get this thing moving, we need to accelerate it very quickly. Well, how do you accelerate one of these little squishy balls to get at any real distance? Well, that's the fun part about working in design is we get to do prototyping and figure out the math on how this would work. So first thing I did was I did some of the math to figure out the mass of this ball, the surface area, and the wind resistance, and just how much force it would take to launch it. I realized it was somewhat attainable, and then I realized I was reinventing the wheel. Someone has already done something like this, and it's called a pitching machine. So the first thing we did is we went on Amazon and we ordered up a nice, cheap pitching machine. It was about $24, and this is one you use in the backyard for t-ball practice. It launches plastic balls. Well, we don't use things normally here in design, so I took it apart. So this was the bottom half of the launcher, and it had two motors inside and two rubber wheels. These wheels would spin up, and the ball would go inside. It would get squeezed and then launched out the other end. So step one was to see if this would actually produce the distance that we wanted for our exhibit. And we found it was pretty close. So at that stage, we need to figure out how to make this a robust piece. Now, baseballs are slightly smaller than this ball. So this particular ball is 3.011 inches. So it's a little bigger than 3-inch, and it's a little bigger than a baseball. So it was a snug fit in here. So I took it apart and realized there's just a simple motor inside and a rubber wheel attached to it. So, okay, we can replicate that and make that a little more industrial. So the next stage on was to find a motor that was industrial, something that we could run for long periods of time without it wearing out, because in an exhibit world, these exhibits are always on. So next step was this here. We're gonna have lots of show and tell today. So what these are industrial spindle motors for a CNC machine. So a computer controlled router table. This would be the motor normally mounted facing down. You have a collet in here that connects to a drill bit or a milling bit they would use for milling out the surface. These motors here are rated for about 35 or 40,000 RPM. Well, I needed to figure out how fast this was spinning. So I put a mark on it, and I used a strobe gun, or something called a stroboscope, where I'd point it at it and it would flash a light at a set frequency, and I'd look at the surface of the wheel. I would see the wheel, the line on it, slowly start to stop and then come to a complete stop. At that point, I knew that was the exact RPM because the light flash was happening at the exact moment that that wheel is in the same position every time. And that worked out to be about 1,500 RPM. So that should be easy, especially with something that's 30,000 RPM. I should be able to get that speed, no problem. So I need to figure out a way of mounting these because usually they're meant to be mounted with this block here as one unit onto your CNC machine. So I set out and I drafted up in Fusion this nice metal bracket here. So this metal bracket, I cut it out on my CNC plasma cutter, which I could show you here. And what that does is it uses the force theta matter to blast through the metal to cut it out basically and create a piece for you. So I just use flat sheet metal, plasma cut it out using the CAD file that I designed earlier. So rapid prototyping is something that we love doing in design. 3D printers, laser cutters, plasma cutters, they're great for doing this kind of work. You can quickly get a bracket out to test something. When I first did that, I found that the bracket was wobbling because it was too thin of a metal. And when the pressure of the ball going between the rollers here caused it to flex. So what I did is I added a brace across the front here to stiffen up between the two, which you can see there. And that stiffened this whole bracket up. Now, another thing I added on top here is, see this black line? This is the runner or the runway for the ball. So the ball comes down through here, gets squished between these two rollers and gets launched out. Now, the next question we had to figure out is rollers. Well, these weren't the first ones that we started with. So I'm gonna go ahead and set this down here. The first ones we went with, here we are these. So these look kind of odd. Well, what they are is these are sanding drums for a drum sander. So they're 3-inch by 1-inch. They would have a spindle going through that you attach into a drill press or a high-speed motor. And you'd put your sanding paper on the outside, tighten a bolt down, they would squish out a little bit and hold the sandpaper for sanding. These were rated for 3,000 RPM. So I knew these would be a good thing to try with. So we started with these. And boy, did they work. Nice grippy rubber. They gripped on the ball really well. Problem was they gripped a little too well. If you look closely, the ball here, see all these black marks on it? Yep. those are tread marks. So basically, when we see a car do a burnout, this rubber, when it hit the ball at that rate of speed, was spinning on it and leaving its footprint behind. Well, we can't have that. The balls would start turning black and it would look horrible. So the next stage was to find a wheel that would work. Well, we looked at caster wheels because you always have that non-marking marked on the caster. So it's for hardwood floors, doesn't leave that black mark. Well, that's what we end up going with. So these are non-marking caster wheels. So we looked everywhere for wheels and trying to find a wheel that's ready for the RPM we wanted, that's made of a HDP or a thermoform non-marking rubber was kind of hard. And they usually don't list RPM ratings on caster wheels. I mean, it's going on a chair. So we have to test these kind of things in controlled environments. You put a little enclosure around it for safety, you put your safety glasses on, and you run it up to the RPM you want to run it at and make sure that it holds safe. The good news is this is on a plastic former with the rubber formed around it. It's a really good design that can handle higher RPM. So I took it to our fab shop. We have a fabrication shop located in the basement of the Carnegie Museum of Natural History, which is really cool. We'll do a tour of that someday. And what I did is I found these cullets. I'll try to pull one off here. There we go. And what that says, that's mounted on the bottom side there. It's a bolt basically that goes through the center of the wheel. And then the fab shop machined a little hub to go inside to adapt the two. And when I tighten this down, it squishes between the two and holds on and gives me a nice tight fit. So for prototyping, this is perfect. When we go into final production, the fabrication shop will machine an actual axle for this that mates up perfectly so we can reuse these wheels or purchase new ones as needed. Nice thing about the motors being CNC spindle motors is the end just pops off and you could swap out ends or bits normally. Well, in this case, we can just swap out the wheels. So it makes service and maintainability really easy. Now, the next step was on that bracket is I made slots in it so you could slide the motors in and out. I can adjust the axle, the best way of describing it, the distance between the axles basically. I can adjust the squish factor of how much it grabs onto that ball when it launches it to how much energy is imparted into the ball and not lost as friction or heat in the surface. So we took it out to our Etna warehouse. And this is a place that we store exhibits that have once been built, are planned to be built, or have already been used, and we're storing them for future needs. It's a really cool facility, but it has very high ceilings. So again, we said we needed 24 feet long by 9 foot 11 high to replicate the staircase. So we measured that out, put a rolling staircase with some tape on it, so we knew exactly how high we needed to reach, and we started doing some testing. And we found some interesting problems when we first started. So when you take that motor, so we'll get to that in a moment. When you take this motor assembly and you mount it at a 45-degree angle, which was the optimal angle for a projectile to go as far as possible. Well, we ran into a problem because when I had this fitting attached like this, can you see the problem? Gravity became the issue. So I'm gonna go ahead and set this down again. When you have your pipe like this and you put a ball in, it doesn't go anywhere. It's because gravity's holding it in place. It doesn't want to come out the other end. Well, this is where things got interesting, and we're going to touch on that after I explain the other method we came out for shooting. So there's more than one way to throw a ball, and the next step was an air cannon. Well, we can't really use an air cannon because you need an air compressor, a tank, and I feel like there's a scare factor there for the youngins, if you will, or the young kids to having that explosion going off. So we needed more like a constant air cannon. So the first step we did is we went and bought a big fan. So let's see if I can pick this up here. I picked up this guy. This is a giant fan. So inside, almost dropped it. Inside here, this housing is a large impeller blade that spins the air, flings it to the outside, and then it comes out this output here and goes out. So what would this be used for? Well, this particular style of fan is called a blower, an air blower, for obvious reasons because it blows air. But this particular one is used for inflatables. Like, those big bouncy castles you have at a birthday party? That's what these are for. These are called high static pressure blowers. And they're really cheap to come by because they're used for inflatable toys, stuff like that. Everybody has them. So we've learned through past exhibits when we've designed things where we need to move, things like balls through tubing. There's a lot of static pressure or resistance to that ball moving that you need to overcome. So a normal fan, which I don't have one here. Oh, actually I do. So a normal fan with blades on it like so, when it encounters a static pressure on the other side, this fan has a lot of gaps in it. And you can see the air can kind of work its way back out. There's not a good way of holding it there. And with high static pressure, as the air stalls, the cutting edge, the leading edge of the blade has a hard time grabbing more air to pull it in. Whereas this is like a centrifugal blower, it uses physics. As the air gets pulled in here, let me start that. As the fan blade's spinning, it has vanes on it. They're mounted kind of like this, like a big paddle wheel. When it's moving, that air that's on the outside accelerates and gets flung outwards. Well, as it does, that causes low pressure to pull more air in from the outside. And by flinging that air out, you're using the mass of the air to get pushed outside here. So that mass of the air is what's actually creating the pressure, or pushing against the pressure. So you don't have that blade attack angle problem. It's a really great way of going about fixing that particular problem. So we have a blower. Why not just put some balls in there like so and just launch them out? Well, that's the fun part. That worked. But we had to find a barrel that would work with. So we went and found standard PVC pipe. And the problem was the balls didn't fit in the end. They were too big. Standard PVC pipe with 3-inch is 3-inch ID, inside diameter, this size. Well, these balls are 3.01 inch. Didn't fit. So we had to kind of go back to the drawing board on that and figure out, what are we going to do? Well, being the exhibit designers, one of our designers, Brian, who works with all the blueprints and everything and comes up with the concepts for these exhibits, he has a long history of material science. And he said, why don't we go with cast acrylic? So cast acrylic, you can get in tube form, and it's clear. And it's a very thin wall because it's actually cast plastic. It's thermoplastic. And it's a really cool material. The nice part about it was it made it up to standard PVC fittings. And because the inner wall was thinner, 3.25 inch or 3.25 inch, the ball fits in there perfectly. So at this point, we had our ball, we had our barrel. So we hooked it up to the cannon, launched the ball. Things were looking great. So we're all excited. This is going to be good. But then we realized, how do you get the ball in? So if you have it hooked up and you have your blower here and it's touching and it's blown out, what would you do? You'd have to turn the blower off, feed the ball into the end of the barrel, turn the blower back on, and have it launch out. Well, we can't have that. It's got to be fun and easy for kids to use. So the next step we did was we got a T-fitting like this. And we put our blower at this end, we put our barrel at this end, and we fed a ball in from the top. That didn't work. The reason that didn't work is because pressure. We have this high pressure flow coming in here. You have a barrel here. That barrel has some resistance to it of the air moving. Well, that barrel is longer than this input shaft. So that causes more resistance than here. So the air was taking the easy way out and was coming out the top. So you try to put a ball in, it just blows right out. It doesn't want to go down into the stream with the air coming out. So how do we overcome that? Well, this is where some physics comes in. We had to use something called a venturi. Now, that's a very technical name for a device that's actually quite complicated. It uses shapes of the tube to shrink it down to take the low velocity, high volume air and compress it down to a low volume, high velocity air. And as that air exits back out, it spreads because the pressure, like I said, wants to take the easiest route possible. When it does that, it creates low pressure. That low pressure is the key. So the first thing I did was I took a T-fitting. This particular one is for a dust collection system. I apologize, a little hard to see there. And I needed a way for the blower to make a venturi. So I used this little rubber gasket here. This is something we had laying around from an air system. It's larger on one side than it is the other. I took that, mounted it to the blower, and put it inside the pipe here. So I'm going to show it on front just so you can see it. And what that did is it caused the air coming in. So I'm going to use this white one here just to make it a little easier. It's smaller than the diameter of the pipe it's going into. That compresses the air down, makes it a high velocity. So it's shooting past this tube at a very high velocity before it starts to expand. That creates a low pressure on this end that actually sucks the balls in. This worked really well. Well, the problem with this was the ball is coming in, it slams down. You can actually hear a thud when it gets to the bottom and then has to be accelerated out by the blower. That change in velocity is not very gradual and you lose some energy there. So the next step was to figure out how to make this work. So this is the fun part. This is when we go to like a Home Depot or a Lowe's and we go in with our blue plastic ball and we figure out what fittings will work and fit. And I came across this fitting. This is called low heel fitting because it looks like it has a high heel, like, you know, for shoes. And this fitting did everything I needed it to do. It had a gradual curve. So when the ball comes in the top here, it can pass smoothly and change direction in the direction of the blower. It had the reduced input side. It was equal to this. So it could compress it down and then it's straight through. So that air coming through at a very high velocity out here. And as it expands, as soon as it reaches that spot, right at that moment, we have an intake. This becomes the vacuum part, the suck of the blow of the air coming out. So this, in a way, combined with our blower, created a venturi. So we're using plumbing hardware. This is for a drain. This would normally be used in a sewer system. So like your toilet or drain would be coming in like this and going down. Well, this would be your vent stack going up. The vent allows the fluid to go down without creating a vacuum. So I'm actually using it, a non-vacuum preventer as a vacuum generator, just in a different method. So this is part of the fun part about doing design. So now that I had, take that fitting off. Now that I had this, it was time to test that out. Well, how do I connect this to the blower? It's got a much smaller fitting on it. So that step was to take a small piece of PVC pipe here, mate that on, and then I found this. This is a size adapter. The nice part about it, it had an angled input on it, which is kind of hard to see there. So when I mount that onto here, it gives me a tunnel, an angled funnel, if you will, that air gets compressed down, sent in, and then up through. So the blower itself is built for inflatables. So it wasn't meant to connect to PVC plumbing. So I'm using something here called a Fernco. It's a rubber adapter tube with 2 hose clamps on it for connecting to pipes that are slightly different sizes. This one happened to be close to 4-inch. So the nice thing about that was I plug that into there, tighten these 2 clamps down. My blower is now taking the low pressure, high volume air coming out of the blower, compressing it down to that high pressure, low volume, going through that venturi, and then being expanded out here on this side. So I'm gonna go ahead and pull that back out to make this a little easier to show. So now that we had this figured out, we would take a clear piece we had, put it in as our barrel, and then we would take a ball and we'd feed it in and see how it launched. Well, 1 out of every 10 were perfect. I mean, it was amazing. It was launching these balls with some velocity, which was really exciting just using that simple venturi trick. The problem we started running into is this barrel is just slightly bigger than the ball. So you can see how it bounces around inside. Well, when it was over here, air would rush past that side. When it was on here, air would rush past that side. Well, we started getting into something called the Bernoulli principle at that point. So when it was slammed against this wall and there was a gap over here, the air rushing over was doing that venturi effect, where it was expanding out here, creating a low pressure volume, which would suck the ball over. Well, then this side would open up. Air would shoot past, creating a low pressure, sucking it over. The ball would oscillate coming out of the barrel, and it would just coming out. We lost so much velocity to that. It's really hard for you to see, but this barrel is full of marks on the inside from the balls bouncing around inside trying to get out. So this was a problem. So the next logical step was, let's go with a bigger barrel. So I went with a 4-inch barrel here and put the ball inside. And you can see there's a lot of room around it. So hopefully that would be a lower velocity, creating less oscillation of the ball. Totally did. That was cool. Well, here's the problem. We lost a lot of distance because there wasn't enough air actually pushing the ball. A lot of it was just escaping around it. So we didn't have the oomph from the air we needed to get the distance we needed. So we had to go back to the drawing board. So I spent the day at a Home Depot going around trying all the different types of pipe. We went to the HVAC section, tried different air ducts, those metal ducts. We went to the chimney section, trying different chimney connections, ceramic pipes, you name it. Went to the plumbing section. We looked at agricultural for like underground drainage. We went and looked at regular plumbing, PVC, ABS, copper. Even went to the electrical section, look at conduits, which we found something kind of close, but just trying to get something that would fit this ball snug, but not too snug. And then we found it. This is called underground PVC. Now, this is something I didn't know existed. This is the fun part about working in this job, is you get to come across these neat things. Underground PVC is a smaller diameter. It's 2 1/4 inch as opposed to 3-inch OD, or 3.5-inch OD, and it's got a very thin wall. Well, that aside, it fit the ball perfectly. So the ball could actually roll in there, but it had a nice snug fit to the point that if I put my hand on here, the ball just now hit the bottom. It's a very, very airtight fit without catching the ball or getting it stuck inside. Well, here's where we ran into a problem. Take a standard PVC pipe, doesn't fit. All right, so now we got to figure out that problem because we got a barrel that works, we have fittings that work, we need to make them mate. So there is something that's kind of rare out there. It's called a schedule adapter, which is this guy here. So what this does is this connects my effectively Schedule 20 PVC pipe, the underground, to the above ground Schedule 40 PVC pipe, and allows me to mate these together to give a tight fit. So once these are all glued together, you end up with a nice tight fit. So back to this guy with our clear barrel. Well, we already have this material. We don't want to waste it. That now becomes our input pipe. Our new barrel material, this now becomes our output pipe. So now when the kids are putting the balls in, they can see them drop in, and then the air cannon launches them out this barrel. So we had to figure out what size barrel we needed, because the physics of that's actually really fun too. It's a projectile science. So the longer the ball spends in the barrel, the more time it can accelerate. Because you're taking that mass and you're accelerating it over time. So the longer that barrel is, the more energy is imparted to it, the faster it comes out the other end. So we tried different length barrels. So the first barrel I did, which won't fit in camera, was 4.5 feet. Then we cut it down to 3.5, and then we did a 2.5 foot. And this was great. It was iterative. We could test different processes to see which one would work. So again, went out to our Etna warehouse. We set up the barrels, taped it out, and see which one will work. Well, the 3.5 foot one slightly over launched by about 3 feet. So it was a little bit too far. So this one will get cut down. Well, we then took the barrel. We tried our 2.5 foot one. And this one fell about 4 feet short of the target. So we knew it would have to be between those two. So perfect science there. Well, then we realized we could do 3 blowers. We could skip the pitching machine and just change the different lengths of these. So if we went with one that was even like 4 inches long, the ball would only go about 10 feet. So there's some great science there because we're looking for concepts that are easy for younger children to understand. Now, barrel length is somewhat easy. If we painted in different colors, we had like a green, a yellow, and a red barrel, we could display on a graphic on how the longer barrel allows the ball to go faster based on the amount of time it spends accelerating. Now, that's a cool science, and it's easy to understand by most kids. Sometimes a pitching machine like that can be a little bit complicated. Speaking of complicated, the electronic side of things, like I mentioned, with mechatronics, you're dealing with the computer science and all the hardware and everything. I'm gonna move this out of the way. This here, I can get it into, this is the controller for those wheel motors. Remember those ones I showed you earlier? These guys? You have to have your motor speed controllers because they're 3-phase induction motors. The reason I went with 3-phase induction motors is there's no brushes. So a DC motor, a direct current motor, has carbon brushes that run on something called an armature that actually wears away. So that material slowly wears away. So if you have a motor running all day, every day for months on end, those brushes wear down and you have to replace them. We don't want to have to deal with that kind of maintenance. So these particular motors, instead of having 2 wires, have 3. These 3 wires are called 3-phase power, and by sending pulses slightly a few degrees away from each other, it's much more complicated than I want to get into for this video, you could pulse that motor around and create that full circle or that alternating current it needs to spin, which is really cool. Otherwise, in a DC motor, that armature changes the field as it's rotating to alternate it. So a DC motor makes its own alternating current to run in a circle. The cool thing about the controller was we have knobs on it and we can adjust the RPM. And there's 2 displays here that read out the RPM. So when we were out at Etna doing our testing, we found that 3,000 RPM wasn't quite enough. It's still falling a little bit short. So we added a couple thousand, or 1,000 RPM, we made it up to 4,000 RPM. And at that speed, the balls were working great. Now the problem we ran into with that, like I mentioned, I told you I'd get back to, was the balls going in and getting stuck. How do we take care of that? Well, we learned the blower machine worked really well. So if we took that device, like so, and we just put a longer end on it like so, and we extended that down to, I have things piled up everywhere here. So we extend that down to this fitting here, and then we take a normal fan and made it up to the back side like so. What that does is that gives an air assist or a boost through here. Not enough to launch the ball, but just enough to push it that extra 1.5 inches forward to hold it right about here, right where it needs to engage with those wheels to launch it out. What's really cool about that is, since it is working like a Venturi, if those motors die or are off for any reason and a ball comes in, it'll stop right there at those wheels. You got to put a second one in because this is blocked. Remember we mentioned earlier the path of least resistance? When this is blocked, that air gets pushed back out and it launches the second ball back out at you. Not at a high speed, but it's enough to let you know that you can't put more in. So it's kind of like a self-fixing system. Once you get those motors going and that ball gets launched out, that path opens up and allows more balls to come in. So it's a self-restricting system that works really well. So we end up using the same fitting for both the ball launcher and the air cannon, which is really neat. So we now have our 2 methods to figure out how we're going to launch this. Now, our third one, which we haven't really gotten into final production yet, we started playing with things called air gates. This is called a blast gate. And we're making an airlock. So the ball would go in, you'd have 2 of these, and then there'd be a tube connecting the 2. And then one would open up, the ball would drop down, that would seal, the next one would open up and drop it in further. This allowed you to make an airlock for the systems. This ended up not working out. Again, we ended up using the Venturi system because the Venturi acts like an automatic airlock by allowing that suction pressure come in to interject the ball into the airstream. So we ended up not needing this. And by the way, if you're ever looking for something like this, a blast gate can be purchased at a hardware store. We got this at Rockler, and this is used for a dust collection system for like a woodworking shop for collecting the sawdust coming off a machine. This allows you to open it and close it depending on which machine you're working on so you don't lose your low pressure in the system. Now, something we use a lot when we're exhibit prototyping is something called gaff tape. It's kind of hard to see here. Think of it like black duct tape, but it's much better than that. This is used in the movie industry. If you ever see a gaffer listed in the credits, this is what they use. So gaff tape is a fabric tape. So I'm going to peel it off here. And it's woven kind of like a, I don't know how to describe it, like a fabric material on the outside. You can kind of see the gloss there. And then it has a non-marking residue tape. So the adhesive on here doesn't leave marks, which again, why they use in the movie industry, you tape cables down, stuff like that. So if you leave it on for anything less than, I'd say maybe 3 weeks, there's no mark. It'll just peel right back off. It's incredibly strong. You can actually use it to patch holes in jeans. Like, it's really strong. But what's nice about it is if you line up with the fabric edge, rips really easy. And if you need to rip perfectly straight lines, gaff tape lets you do that. It's an amazing versatile material. A little bit expensive, but if you're ever doing prototyping at home and you need a tape to make up fittings, because for example, before I had this schedule adapter, and this wouldn't quite fit in there, I was able to take gaff tape, stick it on, and make up a temporary gasket to prove the concept that this barrel worked before I had to go and buy a fitting to hook it up. And you can just peel it right off without leaving a residue. So gaff tape is a very good tool for when you're doing prototyping like this. So I think that, I'll get everything out of the way here. I think that covers everything we went through to get this exhibit to where we are today. Now, next step is building it into a cabinet, because we always have to make it nice and neat. So we're gonna use soundproof material, which we've used in the past to deaden the sound of a blower. And all it is it's a foam material with triangles on it. The foam absorbs more of the higher frequencies, the triangles absorb more of the lower frequencies, and it converts that sound energy into heat. And that makes the cabinet quieter, so it's not as scary for younger children. So we're working on that. The next stage too is we had to figure out what angle this needed to be at. And we found that about 43, 44 degrees was the ideal angle for launching these balls at. Well, we can't have the blower sitting right where the kid would be standing. So the next step was we needed this to make a bend to come down. So we found these nice 45-degree angles that fit in nice and snug. So that way the exhibit wall can be right here. And you have your tube coming down like so, that goes down to the blower, which is in the base of the cabinet. So only from here up is sticking out the top of the cabinet. So from there, we can mount our clear input barrel. And again, we'll shorten this way down. And then on the end of it, we'll put a size adapter. This is from 3 to 4. And that will live on that little barrel like so to give a nice smooth edge for the fingers when you're pushing a ball down inside. So that stage is the fun stage, but it's kind of boring because I say we're just building a cabinet. But I'll be sure to update you guys whenever we get to that stage, maybe even in installation so you can see how they fire. We have a third one in the works. I don't want to spoil it. That was going to be a surprise. But this is a quick walkthrough of what it's like to be an exhibit designer at the Carnegie Science Center. I hope you enjoyed this behind the exhibits tour today. Thanks for watching.